Welcome to this comprehensive course on signal and systems. In today's interconnected world, signals are the lifeblood of communication, control, and computation. Systems are the frameworks that process these signals, enabling everything from phone calls and radio broadcasts to robotics and artificial intelligence. Our goal in this course is not just to define what signals and systems are, but to give you the intellectual tools to model, analyze, and manipulate them in practical contexts, whether that's in electrical engineering, communications, biomedical engineering, or any field that relies on signal processing. This is Module 1, where we'll focus on the foundations of signals and systems and develop the analytical thinking required for more advanced methods. Section 1, Representing and Classifying Signals. Let's start with a fundamental question: what is a signal? A signal is simply a function that conveys information about some phenomenon. It could be a voltage varying with time in an electrical circuit, a temperature reading from a sensor, an audio waveform captured by a microphone, a sequence of pixel intensities in a digital image. Signals can be classified in many ways, depending on their nature, representation, and application. 1. Continuous time and discrete time signals. Continuous time signals, defined at every instant in time, like an analog audio signal. Discrete time signals, defined only at specific time intervals, like a digital recording. 2. Periodic and aperiodic signals. Periodic, repeats at regular intervals. Aperiodic, does not repeat regularly. 3. Deterministic and random signals. Deterministic, can be described by an exact mathematical expression, predictable. Random, values cannot be predicted exactly, described statistically. 4. Even and odd signals. Even, symmetrical about the vertical axis. Odd, symmetrical in sign change about the origin. In system analysis, classification is not just academic. Knowing whether a signal is continuous or discrete, periodic or random, affects the tools we use to process it. Section 2, Representing and Classifying Systems. A system is any process or device that takes an input signal and produces an output signal. For example, a speaker system converts electrical signals into sound waves. A digital filter removes noise from a recording. A control circuit stabilizes temperature in a heater. Systems are also classified. 1. Linear and nonlinear. Linear, the output obeys the principles of superposition and scaling. Nonlinear, the output response is not directly proportional to the input. 2. Time invariant and time variant. Time invariant, system behavior does not change over time. Time variant, system parameters change over time. 3. Causal and non-causal. Causal, output depends only on present and past inputs. Non-causal, output depends on future inputs. 4. Stable and unstable. Stable, output remains bounded for bounded input. Unstable, output grows without bound for some bounded input. Understanding these properties is critical for predicting how a system will respond to various inputs and for designing systems that meet practical constraints. Section 3, Singularity Functions. Singularity functions are special mathematical tools used to model idealized signals that occur in engineering, such as unit step function, turns a signal on at a specific point. Impulse function, represents an instantaneous spike. Ramp function, a linearly increasing signal starting from zero. They are especially important in system analysis because they can model sudden changes in signals. They form the building blocks for more complex signal representations. They are used in solving differential equations for system responses. Section 4, System Response using Convolution. One of the most powerful methods for determining a system's output given a known input is convolution. Think of convolution as a mathematical way of blending two functions, the input signal and the system's impulse response, to produce the output. Key points. Works for linear time invariant (LTI) systems. Can be applied in both continuous and discrete domains. Provides a direct link between a system's inherent properties and how it processes incoming signals. In practice, if we know how a system reacts to a brief impulse, its impulse response, we can predict how it will respond to any arbitrary input by convolution. Engineers use convolution to design filters, predict system behavior, and process images. Section 5. Fourier series for periodic signals. Many real-world signals are periodic, or can be approximated as such over a certain interval. The Fourier series allows us to represent any periodic signal as a sum of sinusoids with different frequencies, amplitudes, and phases. Why this is important? Sinusoids are the fundamental building blocks of signals in engineering. Any periodic waveform, no matter how complex, can be expressed as a combination of these pure tones. Fourier analysis helps us design communication systems, audio synthesis tools, and vibration analysis techniques. In practice, the Fourier series reveals which frequency components are present in a signal. This makes it easier to analyze and filter signals in the frequency domain rather than the time domain. Section 6. Applying Fourier series to LTI systems. The beauty of the Fourier series in LTI systems is that sinusoids are eigenfunctions, meaning that if you input a sinusoid into an LTI system, the output will also be a sinusoid, only with possibly different amplitude and phase. This makes frequency domain analysis much simpler. You can understand how each frequency component of a signal is modified by the system. Complex system responses can be predicted without doing full convolution in the time domain. Section 7. Fourier transform for aperiodic signals. Why the Fourier series works for periodic signals? Most real-world signals are aperiodic. For this, we use the Fourier transform. Key points. It converts a time domain signal into its frequency domain representation. Allows analysis of continuous signals that do not repeat. Essential for spectral analysis in applications like radar, medical imaging, and music processing. In practice, engineers often design systems directly in the frequency domain. For example, audio equalizers are built by shaping the frequency response of signals. In this module, we've covered the definition and classification of signals and systems, singularity functions and their role in modeling, convolution as a method for determining system responses, Fourier series for periodic signals, Fourier transforms for aperiodic signals. These are the foundation stones of signal and system analysis. In Module 2, we'll move into Laplace transforms, state space analysis, sampling theory, Z-transforms, and the use of MATLAB to put all of this into practice.